Welcome back to Basic Electronics. In the last lecture, we looked at the Ebers-Moll model, which describes the BJT in all modes of operation. We will now use the Ebers-Moll model to plot the collector current IC of a BJT as a function of the collector to emitter voltage VCE. With the help of the IV characteristics, we will take another look at the earlier BJT circuit and figure out the correct solution. Finally, we will look at a circuit with a PNP transistor. So let us begin. We now want to discuss the IV characteristics of a BJT in a graphical form. Now first we note that a BJT is quite different from a diode in that it has three terminals. For a diode we had only two terminals, so there was exactly one current and one voltage to talk about, and therefore the entire diode behavior could be captured with just one plot, the current versus voltage. That is not the case for a BJT. We can look at several different things, and here are some of these. IC versus VCB. So this current IC versus this voltage VCB for different values of IE, IE1, IE2 and so on. Or we can plot IC versus VCE, IC as a function of VCE for different values of VBE, VBE1, VBE2 and so on. Or we can plot IC versus VCE, IC versus VCE for different values of the base current. And of course there are some other ways of plotting the characteristics as well. So the IV relationship for a BJT is not a single curve but a family of curves or characteristics. And we will look at the IC versus VCE curves or characteristics for different IB values, because we will find these very useful in understanding amplifier biasing. What we are going to do is take an NPN transistor and plot IC as a function of VCE, this voltage drop, for various values of IB. And we will do that by solving the Ebers-Moll equations. So the experimental setup would be something like this. A voltage source is connected between collector and emitter. Its value is VCE. So this is going to be our x-axis variable. The collector current IC is going to be our y-axis variable. So we're going to plot IC as a function of VCE. And we will find that IC versus VCE depends very much on what this base current is. So therefore for a given base current, let's say 10 microamps, we are going to get one of these curves, IC versus VCE. If I change this 10 microamps to let's say 20 microamps or 50 microamps, we are going to get another IC versus VCE curve and so on. So therefore the IV characteristics of a BJT, like we said in the last slide, is not one single curve but a family of curves, and that is the complete picture that we want to see. These are the parameters we will consider. Alpha F, the forward alpha as 0.99, that makes beta equal to alpha by 1 minus alpha, that is 99. Alpha R, the reverse alpha, equal to 0.5, that makes the reverse beta equal to alpha R by 1 minus alpha R, or 1. And clearly this transistor is very poor in the reverse direction because this beta is so small in the reverse direction. And these are the saturation currents, IES 10 raised to minus 14 ampere and ICS 2 times 10 raised to minus 14 amperes. First, let us replace the transistor with the Ebers-Moll model like that. And recall that in the active mode we need to only consider IE prime and alpha IE prime, but in general we need to consider all 4 branches. Okay, what we want to do is to get IC as a function of VCE for a fixed value of IB, that is 10 microamperes. What we will do now is to take one specific value of VCE, say 1 volt, and figure out how we can calculate IC for that VCE with IB equal to 10 microamperes. So for convenience, let us take the emitter node as the reference node. So that means VE is 0 volts and VC, the collector voltage, would then be 1 volt because we have taken VCE equal to 1 volt, and we don't know what VB is going to be. So what we need to do is to solve the Ebers-Moll equations for VB, and once we know VB, we know this difference VBE, we also know this difference VBC, and once we know these two voltages, we can find IE prime given by that equation, we can find IC prime, and once we know that, we can find all other quantities. For example, IE is going to be IE prime minus alpha R IC prime, and so on. So we need to get an equation in terms of VB, and what is that equation? That equation is given by IB equal to 10 microamperes. What is IB? IB is equal to IE prime plus IC prime minus alpha F IE prime minus alpha R IC prime, and IE prime and IC prime essentially are functions of VB, because VBE here is VB minus VE. VE is known, 0 volts. VBC is equal to VB minus VC. VC is known, 1 volt, and therefore IE prime and IC prime can be written in terms of VB. So that is the equation we need to solve for VB, and you can see that it's going to be a non-linear equation because we have exponential terms over here. So we need to use some iterative method to obtain VB. So by solving this equation, that is IB equal to 10 microamperes for VCE equal to 1 volt, we are going to find one value of the collector current, and then we repeat this exercise for other values of VCE, and that is how we are going to plot IC as a function of VCE. And here are the results that we obtain. This axis is VCE, this is VCE equal to 0, this is VCE equal to 2 volts. This curve here is VBE, that means the voltage across the base emitter diode. This curve is VBC, the voltage across the base collector diode. This current is IC prime, this current here, and the solid line here is IC, the terminal current, and the dashed line is IE prime, this current here. Let us look at the various quantities of interest at a specific value of VCE, say VCE equal to 1 volt, and let us start with the junction voltages. Here is VBC, and for VCE equal to 1 volt, VBC is about minus 0.3 volts. That means the base collector diode is under reverse bias, and that means IC prime is very small, nearly 0, and therefore this branch is like an open circuit, and so is this branch. And if we look at the IC prime plot, we see that IC prime is 0 at VC equal to 1 volt. Next, let us look at VBE, the base emitter voltage, this plot here, and VBE is about 0.6 volts, maybe between 0.6 and 0.7, and that means the base emitter diode is under forward bias, and therefore our transistor is operating in the active mode, with the base emitter junction under forward bias and the base collector junction under reverse bias. Now since IC prime is 0, IC is equal to alpha f times IE prime. What is alpha f? Very close to 1, is 0.99 for this transistor. So IC is nearly equal to IE prime, and that is what we see over here. IC and IE prime are nearly equal. Okay. Now since we know that the transistor is operating in the active mode, we also know that IC can be written as beta times IB. And what is beta? Beta is 99. So IC is expected to be 99 times IB, or 99 times 10 microamperes, that is 990 microamperes, that is nearly 1 milliamp. And that is what we observe over here. IC is about 1 milliamp. Let us summarize the situation for VCE equal to 1 volt. We have about 0.7 volts appearing across D1, and the rest of the voltage, that is 1 volt minus 0.7 volts, about 0.3 volts, appears across the base collector junction. And since this end is positive compared to this one, the base collector diode is not conducting. Alright, what we will do now is consider another value of VCE, namely VCE equal to 2 volts. For this voltage, we notice that our base emitter voltage has not really changed. We can't really tell the difference. And the entire difference, that is 2 volts minus 1 volt equal to 1 volt, has appeared in VBC. This was minus 0.3 volts and this is about minus 1.3 volts. So the base collector junction continues to be under reverse bias. The transistor continues to be in active mode. IC prime continues to be 0, and our collector current also remains equal to 1 milliamp. So all that has happened as we go from VCE equal to 1 volt to VCE equal to 2 volts is that an additional reverse bias of 1 volt has now appeared across this base collector diode. Earlier, with VCE equal to 1 volt, the reverse bias was minus 0.3 volts, and with VCE equal to 2 volts, it is now minus 1.3 volts. Apart from that, there is no real change. Let us now look at what happens when we change VCE in the other direction, let's say from 1 volt to 0.5 volts. And let's start looking at the diode voltages first. Now VBE has not really changed. It has remained at about 0.7 volts. VBC has changed from minus 0.3 volts to about 0.2 volts. So the entire change in VCE has actually got reflected in VBC. And IC prime continues to be small. Note that VBC has now become slightly positive, but it is not large enough to make IC prime substantially or significantly large, and that is why on this scale IC prime is still looking like 0. So the transistor continues to be in the active mode, and IC continues to be about 1 milliamp, that is beta times IB. At about 0.2 volts, somewhere here, the current IC prime starts rising because the forward bias across the base collector junction has now increased to make IC prime significantly large. Apart from that, there is also a slight reduction in VBE, as we see over there. And because IC is alpha f IE prime minus IC prime, this current is now decreasing because VBE prime is going down a little bit, and this current is increasing there. What happens is IC now starts going down like that. So we have two distinct regions in the BJT IV characteristics. The right side of this line is the so-called linear region, which we have been calling as the active region as well, and we are already familiar with that. The left side is the saturation region. Now this region is new to us. In this region, both the base emitter and base collector junctions are under forward bias, and the collector current is less than what it would be in the active region. So let us summarize these observations. We have a linear region, the right side of that line, in which the base emitter junction is under forward bias, base collector junction is under reverse bias, and IC is beta times IB. And in this example, it is about 1 milliamp. We have the saturation region on the left of this line, and in saturation region, the base emitter junction is under forward bias, and the base collector junction is also under forward bias. And in this region, IC is less than beta times IB, as we can see over here. So here is the IC VCE curve for 10 microamps again. And in the linear region or the active mode, the collector current is beta times IB, which is about 1 milliamp. Now we want to look at the IC VCE curve when the base current changes from 10 microamps to 20 microamps. So let's look at the results. That is the IC VCE curve now for 20 microamps. And we see that it has not really changed much in many aspects, except in the linear region, IC has become 2 milliamps, approximately 2 milliamps, and for 10 microamps it was about 1 milliamp. And this of course is expected because in the linear region we have IC equal to beta times IB. Beta is about 100, so 100 times 20 microamps, that is 2 milliamps. So this part is really expected simply from this equation. And the boundary between the linear and saturation regions has also not really changed. The transition is happening at about the same VCE value, about 0.2 volts. So as we go from IB equal to 10 microamps to IB equal to 20 microamps, there is a large change in IC from 1 milliamp to 2 milliamps. That's a factor of 2. And we now want to see how that change gets reflected in the VBE and VBC plots. What is IC in the linear region? IC is alpha times IE prime. So if IC has changed by a factor of 2, IE prime would also have changed by a factor of 2. So let us look at the equation for IE prime now. IE prime is IES e raised to VBE by VT. This one is too small compared to the first term. We won't worry about that. And if IE prime changes by a factor of 2, it calls for a change in this factor, e raised to VBE by VT by 2. Now because this is an exponential relationship, that requires VBE to change only slightly, and that is what we are seeing here essentially. So the blue curve is for IB equal to 10 microamps, and the pink one is for IB equal to 20 microamps. And we see that for 20 microamps, the base emitter voltage is only slightly larger than the case for 10 microamps. And because these two voltages must add up to VCE, that change is also reflected in VBC. So overall, there is a large change in the collector current plot, but there is hardly any change in the base emitter and base collector voltages as we change IB from 10 microamps to 20 microamps. And based on this experience, we can now predict what is going to happen for some other value of IB. For example, if IB is made 5 microamps instead of 10, IC is going to be 0.5 milliamp, because we are changing IB by a factor of 2. IC will also change by a factor of 2 because of this proportionality here. And then we will get a curve, IC-VCE curve, which looks like this. And we don't really need to do that calculation. Similarly, if IB is 15 microamps, that is between these two values, IC would then look like that. And all of these curves will cross over from linear to saturation regions at about VCE equal to 0.2 volts. Let us now revisit this circuit that we have looked at before. And if you remember, when RB was changed from 100K to 10K, we found that active mode was not possible anymore. And now, having studied the IC-VCE characteristics, we would be able to explain what happens. So we are now in a position to explain what happens when RB is decreased from 100K to 10K. So what we will do is we will plot IC versus VCE for two values of IB, 100K and 10K. And as we have seen earlier, if we take this voltage as approximately 0.7 volts, then RB times IB is 2 volts minus 0.7, so that is 1.3. So IB is 1.3 by 100K or 1.3 by 10K, depending on the value of RB. And let us now look at the IC-VCE characteristics for these two base currents. So here is IB equal to 13 microamp, which corresponds to RB equal to 100K. And what would be the collector current here in the linear region? That would be 13 microamps multiplied by beta. That is 1.3 milliamps, and that is exactly what this is. When we change RB from 100K to 10K, our base current goes up by a factor of 10, and it now becomes 130 microamps. And now the collector current in the linear region is 130 microamps times 100 or 13 milliamps. So this collector current is now 13 milliamps. Now whatever solution we find for this circuit, that is the value of IC and the value of VC, must satisfy either this constraint imposed by the transistor if RB is 100K, or this constraint if RB is 10K. And note that VC here, this voltage, is the same as VCE because the emitter is at 0 volts. Now apart from that, there is one more constraint that we need to worry about, and that is imposed by this resistance RC. So let us see what that is. So in addition to the BJT IC VCE curve, the circuit variables must also satisfy the following constraint, and let us see where this is coming from. VCC equal to VCE plus ICRC. VCC must be equal to this voltage plus this voltage. Now this is just VCE, that is this variable here, and that voltage drop is ICRC. Now this equation essentially looks like a straight line in the IC VCE plane, and let's plot that straight line now, and that is what it looks like. Its x-intercept is 10 volts, and that is obtained by putting IC equal to 0. If IC is 0, then VCE is the same as VCC, which is 10 volts, and its y-intercept is 10 milliamps. And if we put VCE equal to 0 now, we get IC equal to VCC by RC. VCC is 10 volts, RC is 1K, so that is 10 milliamps. So that is the graph of this constraint, which is imposed by RC. The intersection of the load line and the BJT characteristics gives us the solution for the circuit, and that is because the solution has to satisfy the load line constraint as well as the constraint imposed by the transistor IV, and that constraint is given by this curve for RB equal to 100K and by that curve for RB equal to 10K. Now for the first case, RB equal to 100K, that intersection is somewhere here, and as we have seen earlier, the solution is VCE equal to 8.7 volts and IC equal to 1.3 milliamps. In the second case, that is RB equal to 10K, we note that the intersection of the load line and the IC-VCE curve happens to be in the saturation region, not in the linear region, and that is why we found that linear region was not possible when we tried to solve this same problem analytically. So what is the solution now? So the VCE is between 0 and 0.2 volts. We often take this approximately as just 0.2 volts, and so therefore we have a voltage drop of 0.2 volts here. This is 10 volts, so 9.8 volts will drop there. So 9.8 divided by 1K, that is 9.8 milliamps. That would be IC. So that is the solution, VCE of about 0.2 volts and IC equal to 9.8 milliamps. So sometimes these graphical methods are very useful, and they help us to visualize things much better than an analytical approach. Let us take this example with a PNP transistor. Assuming that the transistor is operating in the active region, we want to find RE and RC such that IE, this current here, the emitter current, is 2 milliamps, and VBC, this voltage, is 1 volt. And we are given that alpha is nearly equal to 1. Now to begin with, let us first check that this condition, VBC equal to 1 volt, does indeed correspond to the linear region or the active region. So we have P and P here, so this is an N region, that is a P region. VBC is 1 volt, so VB is higher than VC by 1 volt, so that means the N-type region is higher than the P-type region by 1 volt, and that means reverse bias. So this junction is indeed under reverse bias, and now let us calculate RE and RC. So in this loop, we can write VEB, this voltage drop, which is going to be 0.7, minus this voltage rise 5 volts, plus IE times RE equal to 0, and that gives us IE RE equal to 5 minus 0.7 or 4.3 volts. And since we are given the value of IE 2 milliamps, we can find RE turns out to be 2.15 K. For the corrector resistance, the RC value here, we can write a loop equation for this loop: VBC plus ICRC minus VCC equal to 0, and that gives us ICRC equal to VCC minus VBC. And since alpha is nearly equal to 1, IC and IE are approximately equal to each other, and therefore instead of IC here we can use IE, and that gives us RC. So IE times RC is about 5 minus 1, and that gives us RC equal to 4 volts by IE, which is 2 milliamps, so that is 2K. In conclusion, we have seen how to represent the behavior of a BJT with the help of IV curves. We have used the IV characteristics to obtain a graphical solution of the BJT circuit, which we have considered earlier. We have also taken up a circuit with a PNP transistor and seen that it can be analyzed in much the same manner as an NPN transistor circuit, if we are careful about the current directions and voltage polarities. Having looked at BJT basics, we will now start looking at an important topic, namely amplification. That is all for now. See you next time.